So I want to welcome all of you here to the Valley of the Shadows of Research Method. This is a research methods designed specifically for business analytics. And my goal today is to walk you through hypothesis testing. Everything that you need to know about hypothesis, generally and specifically for research purposes. I'm going to walk you through that. Now, the way I'm going to go through this is in such a way that if you could interrupt me, it will help me to slow down. So do not be worried at all interrupting me. When something is not clear, let me know quickly. What is a hypothesis? A hypothesis is a claim about a population parameter. NDC will win the next election. MPP will lose the next election. That is a hypothesis. The only thing is that it depends on who is making that hypothesis. A hypothesis is a very, very powerful situation that we use in all kinds of research because it's part and parcel of our lives. Now, point estimates a specific number and confidence intervals, two numbers, with one being a lower number and one being a higher number. These are basic inferences tools that are used as the foundational blocks for inference techniques. Now, that framework for determining whether an observed data deviates from the expected variable, that process, that framework is what is known as statistical hypothesis. It's an assumption, it's a claim, it's a guess about a population parameter. It's a conjecture. So let's take an example. If you want to find out the mean delivery, the average delivery time of an online food, you order food or you order for a taxi or Uber, the time it takes for the taxi to get to your house, if we say that the average is 30 minutes, that is a hypothesis. If you make that statement, that's a hypothesis. But then it depends on who is making the hypothesis. That's why we have two types of hypothesis. So in hypothesis, you have a population parameter. A parameter can be, it's a statistic. And you have that population parameter. Is this a population because it is representing everything? And from that population, you can take a sample to judge about that population parameter. You check whether the value that you are going to have is significantly different from the sample statistic that have been computed from the data you collected. So normally, Kokubako will pick up data, as you can remember, to justify his point that he has made on the radio, to say that that statement I'm making, I am certain with 90% confidence, which means I am not certain with 10% confidence that this is a situation. So hypothesis testing is being used a lot in so many disciplines, from archaeology to zoology, from mathematics to quantum mechanics, okay, from humanities to all sorts of areas. We want to test a new automobile system, whether that automobile system increases the mean miles per gallon performance. That is a hypothesis research. You want to validate a claim, like a manufacturer claims that, 1 liter soft drink bottles are filled with an average of at least 0.999 liters. You want to validate that claim. You want to test a business decision, okay, whether new online advertisement has led to higher online conversion rate for an e-commerce website. You want to validate that. And these are all hypotheses. Now, in hypothesis testing, you need to make a statement about a population parameter. You got to make a decision as to whether you are dealing with a null or the alternative hypothesis. Now, what is the difference? The purpose of a hypothesis is to check whether the null is likely to be true, given the sample data. That is the main thing. The null is written as HO, okay? And it's always, and you got to keep this in mind because it will come back to you all the time. the null always carries some level of equality. And so when you have, there are 6 symbols that are used for hypothesis testing. 6 symbols. For example, let me ask you, what do you think is the opposite of equal to? Quickly. You can quickly shout the answer quickly for me. Guys, be fast for me today.
Not equal.
It's not equal to. What is the opposite of less than?
Greater than.
Okay, that is not correct. What do you think will be the opposite of less than?
Not less than.
Exactly. But what is not less than?
Greater than or equal to.
That is the point. So opposite of less than is greater or equal to. Keep that in mind. Document it. Write it down. Opposite of greater than will be what? Opposite of greater than. Quickly, 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 quickly. These are the easy part.
Less or equal to.
Less or equal to. Okay. So these are very important. Now watch these ones. These two, okay, the one on the left here, these two are known as two-tail testing. And then these ones, these 4 here, because they take one direction, are one-tail testing. What do I mean? Take for example, when you take less than or equal to and not equal to, one of them is the null hypothesis. Now, looking at the statement I've documented below here, the statement says the null always carries some level of equality in it. So between equal to and not equal to, which one will have the null hypothesis? Which one will have the null hypothesis? Is it the equal to or the not equal to? I need quick answers, guys. Otherwise, I'm going to fly and in a way that you might not understand. That's the only way you can stop me.
I think it's the equal to.
The equal to carries some level of equality. Now, between less than, okay, and greater than or equal to, which one will have the null hypothesis? It is a greater than or equal to. And the same thing goes with this very other answer. So keep that statement in mind because that statement is very, very important. And I've described it here. So in a one-tail testing, your focus is on the bending, either bending to the left, bending to the right. But then in the two-tail testing, you are more dealing with using the alternative hypothesis. Remember, you always have to use the alternative hypothesis. Now, if you look on the symbol here, there is a mu and there's a mu naught. The mu naught is the hypothesized mean. Okay. And so what you are saying is that the mu, which is the mean, the average, is not equal to the hypothesized mean. And these ones are the alternatives. Okay. All of these symbols, okay, are the alternatives. And it is the alternative that you can use clearly to determine the tail of the test. Because the alternative, for example, for not equal to, that will tell you that it is two-directional. Because if something is not equal to a number, if I say you are not equal to, your age is not equal to 30, that means your age is either above 30 or below 30. That is two-direction, above 30 or below 30. So therefore, because it's two-direction, we choose the two-tail test. It's very important to note these things. Okay, which one do you think is more powerful? One-tail test or two-tail test? You will later realize that it's two-tail because it carries the others within. Okay, let's look at the steps in hypothesis testing. The steps. Okay, we have 2 kinds of. First, you identify a key research question. So you have a research question. Remember, a research question has a question mark. A hypothesis has a statement. You can take any research question and convert that question to a hypothesis. For example, what is the effect of corporate social responsibility on bank profitability? What is the effect of corporate social responsibility on bank profitability? That is what? A question. Let's make it a statement, a hypothesis. Corporate social responsibility positively affects bank profitability. That's a statement. That is a hypothesis. So every research question could be converted into a hypothesis. Okay? From that, you can deduce the hypothesis. And once you make it a null hypothesis, the alternative hypothesis will follow through. Once you establish the hypothesis, you have got to understand and prepare the data. Go collect data. In our case, quantitative data. You got to understand the data. You got to know the variables, not just data, but know the variables within the data. And ensure you can collect data before you even start thinking about, the nature of your topic. There are some of you, the topic you've chosen alone will not allow you to get the right data. Then you identify the right test you are going to use. And we shall see examples of that today, which kind of test to use. Choose the method for testing on the last 3 points. That is the data you collected. Ensure that all assumptions are satisfied. Today we shall check whether an assumption is satisfied. Remember, we are going to use the Brukutu Venture data set, and then you can perform the test itself. Now, it's the same thing I put here in a diagrammatic fashion. Formulate a null and alternative hypothesis. So when it comes to specific hypothesis process, this is how you go around it. Formulate a null and alternative hypothesis. We shall do an example right now. Select the test, choose the level of significance. Now, what is the level of significance? The level of significance is the probability of committing a type 1 error. But let's put that one aside so that you can appreciate it. You see, anytime you are doing a research, you are likely to make some mistakes. For example, if you make a statement that NDC will win the next election, you are likely to make a mistake, a modicum of mistake in your statement. Now, there is a certain amount of error you are allowed to take, you're allowed to make. The mistake you are expected to make is the level of significance. The mistake you actually make, not the one you expected to make, but the mistake you actually make is the p-value. Note it down. People don't explain these things easily like that for you to be able to appreciate it. So the error you expected, you are allowed to make is the level of significance. So you got to know the level of significance before you even undertake the research. You got to know, you got to choose alpha prior to undertaking the research. And there are 3 of them, 1%, 5%, and then 10%. So you select that. Now, in most softwares, the default alpha is 5%. So in Excel, we'll give you 5%. Okay? We'll specify most of the softwares we are using are Python, right? So we also use the same 5%. But just know the difference between the p-value and the alpha. The p-value is a mistake you actually make. So we'll judge that. Now, which one would you wish it is smaller? Is it the alpha that should be smaller than the p-value, or it is the p-value that should be smaller than the alpha? Which one? Which one? Which one should be smaller than the other?
The p-value.
P-value
Exactly.
should be smaller than alpha. Exactly.
The p-value has to be smaller than the alpha, because when it is smaller, then you have enough gravitas to reject the null hypothesis. Now, another angle you can use to do this is known as the critical value and then the test statistic. Now, the same thing. The test statistic has to be bigger than the critical value to be able to have enough confidence to reject the null hypothesis. Because again, the test statistic is your information gathering numbers. Whereas the critical value are things from the table, the benchmark against which you judge your test statistic. So that is why you can see on the right here, you compare that test statistic with the critical value. And then here you compare the p-value with the alpha. Now, based on the comparison, you can now reject or not reject the null hypothesis and conclude in favor of whichever one. Hypothesis testing, steps done. In the process, you commit some kind of errors. We have the type 1 error, and we have the type 2 error. Type 1 error and type 2 errors is very simple. The type 1 error is a probability of rejecting the null hypothesis. The type 1 error is what is known as the alpha. Is rejecting a true null hypothesis. So if you check here, okay, if you check on this one, the null hypothesis is true, and then you mistakenly reject it. I mean, how on earth could you do that? The null is true. The null is true. What the government, what the authority said was true. You rejected that. You committed a type 1 error. Boom. Now, the type 2 error, the null is not true. It's false. And you're supposed to reject it. But you fail to reject that null hypothesis. You commit a type 2 error. Big mistake. Make sure you don't fall into some of these errors when you're doing research. So these are some hypotheses. And my job is I'm going to guide you to formulate some of these hypotheses. So you're going to formulate some of these. By the way, do you see my screen?
No, Doc, I think there's an issue. It's still showing application of hypothesis.
Oh my goodness. I have gone through all these. Yeah, this normally happens when people are not concentrating, they are not participating, they are not, following. Because I've done all of this. I spoke about 1 tail, 2 tail. I've gone through every step here, and now I've finished this one there. Then I'm here. I've even just completed type 1 and type 2 error. Okay. When the null hypothesis is true and you reject it, you commit a type 1 error. But when it is false and you fail to reject it, you commit a type 2 error. So when I was showing all of this, you guys were not seeing because people are not paying attention. Well, so here we have some hypotheses I want you to formulate. Okay. Here's a hypothesis. Nescafe claims that since the population mean filling weight is at least 3 pounds per can, consumers' rights are protected. And you guys have this. How will you formulate this null and alternative? How will you formulate the null and alternative hypothesis? Who has a clue? If you have a clue, let me know. How would you have formulated the null and the alternative hypothesis? Well, let me try and put it here. Oops. I think my screen is gone, right? Hold on, let me see. All right. So this is where we are. Okay. We have to formulate the null and alternative hypothesis here. Okay, so there you go. So I'm just going to put this here because this is a Python, and just put it here for you to see. So I'm going to formulate the null and the alternative hypothesis here. I'm going to formulate it mathematically. Okay. Now, the first thing you do in hypothesis formulation is to look for the sentence. So look at it. Nescafe claims that since the population mean filling weight is at least. So the key word here is the word at least. What symbol is at least? Who can guess? What symbol is at least?
Greater or equal to.
Greater or equal to. So let's say that you want to write it like this. I mean, there's a way to write it, but I've forgotten that. But I'm using this one to represent the at least here. Okay. So when you look here, I'm using this to represent. So that's what you write. And then below that, write the opposite. What is the opposite of this? What is the opposite of this? less than. What is the opposite of less than? Greater than or equal to? Well, I've said it. It's less than, isn't it? So the opposite is this. It's less than. So if this one is greater than or equal to, this is less than. Now, watch the sentence. It says that 3 pounds per can. So behind each one of them, you put the number 3. Okay. It says 3 pounds per can. So you can put 3 pounds per can there for each one of them. And then you can take the same number here and put that same 3 pounds per can for this one too. We have not formulated yet. Okay. We have not formulated yet. Now, after you've written that, we need to write the mu because we are talking about population. This is population. So we need to write the mu. I'm going to put this symbol here and write mu for the mu. So mu to indicate the mu. And you do the same thing for the other one. Remember, right now, you don't know which one is the null hypothesis and which one is the alternative hypothesis. But what we know for sure is that the null hypothesis carries some level of equality. So between the top one and the down one, okay, which one do you think? Let me put a colon in front of each one of them. I'm putting a colon in front of each one of them. Now, let's identify which one is the null hypothesis. Is it the top one or the down one? What do you think? Is it the top one or the down one? Oh, by the way, if you want to put everything that you are doing into a mathematical symbol, okay, we can put this symbol here and then write the dollar symbol. If you put a double dollar symbol, the whole thing is going to go into the middle. So I'm going to put a double dollar symbol there. And I'm going to do the same thing for this. Put a double dollar symbol here, just so that it will become mathematically, inclined. So now the top one and the down one, which one will be the null hypothesis? Looking at the symbols. Which one? Remember, the null hypothesis carries some level of equality. It carries some level of, so which is the null? Top or down?
Greater or equal to is the null.
Which is the top one, right? Good.
Yes, sir.
I'll write H underscore 0. The underscore makes it a subscript. And I'll do the same thing for the alternative. The alternative is normally written as HA. So I write H underscore, A, just to make it what? Subscript. Now I'm going to run this. I'm going to just write this. I'm going to run this. There you go. Let's see how it is now written. Because I'm writing it in this. Now you can see that it has come down here. Okay, I made a typo. Oops. This has been flying anytime I try to show. So watch it here. I made a slight typo. Yeah. The column should be after, not before. So H naught colon, and then HA colon. You should be doing the same thing. Okay, stuff I know you don't have. And then remember that we're writing the mu. So let me space this a bit and then write the mu and then run it. So this becomes your null hypothesis. So you can see that mathematically it's been written nicely in a mathematical fashion. Okay. So this is the null hypothesis, which says that the population mean filling weight is at least 3 pounds per can. And the alternative is this. So now you've been able to formulate the null and alternative hypothesis statistically. But remember, you understand it. You understand it, in English fashion. Now, using that principle, that knowledge, you can go ahead and do the same thing for each one of these. Max Flight uses a high technology process to produce golf balls with a mean driving distance of 295. The word off is a symbol for equal to. Is equal to. Was is equal to. Off is equal to. On is equal to. Okay? Most of the prepositions are the same as equal to. So this one will have the null to be equal to, and its opposite is alternative, which is not equal to. So this one, you can easily formulate it. You can just copy this one, dump it here. Okay. So let me see if I can do that quickly. Copy this one, dump it here, and then just change the equal to. Now remember that in this context, the null was dealing with 295. So you're supposed to have here 295 yards. Okay, 295 yards. And you do the same thing. You can copy this and then put it there. And that will be formulated as, these are your exams. Okay, 295 yards. But the symbol is equal to for this, for the top one, because remember it is of 295 yards. And the opposite is not equal to. Oh, how do you write not equal to? You can use the symbol backslash and do neg. Okay, backslash and then do neg and then space it, and that should give you the not equal to. Let's try this. There you go. Okay, so you can see that the equation has been nicely written in a beautiful mathematical format. You have the null here, and then you have the alternative following beautifully like that. And of course, use that same principle to do for this third one. According to the CEO, the new BMW car can run more than 24 miles per gallon. So you got to ask yourself, what symbol is more than? What symbol is more than? Who can tell me? What symbol is more than?
Greater than.
Greater than, exactly. And now you know that this is greater than. Its opposite will be less or equal to. And so you can now know that the now will rather come to the bottom one, because that is the less or equal to. And then the rest, you can do it yourself. Okay. Now, in hypothesis testing, you got to now deal with samples. Samples. We have one sample that you can be dealing with. For example, checking something against a hypothesized value. You can have two samples. You can have three or more samples. That is where the area of ANOVA, whether it's repeated or unrepeated, whether it's Friedman or Kruskal-Wallis, okay, they come into the picture. I have all of this at the end of the lecture. But let's start with one sample. Everything is being done in Python. The distribution of anything, okay, can be used to calculate the confidence interval of anything. But that would depend on whether the population standard deviation is known or is not known. So I want you to check this. We are talking about t-test or z-test. These are the major test statistics that most, hypothesis testing will adopt and use. When the population standard deviation is known, we use the normal distribution with certainty. Now, why? Because when the population standard deviation is known, it means that you are inching towards what is known as normality, because it's like you are taking everything and you know it with certainty. But when the population standard deviation is not known, you got to estimate the unknown population standard deviation using a sample one. So you take a sample from the population because you don't know the entire population. And by the way, when we say population, it's not a human being population. You can have a population of cars. You can have a population of women. You can have a population of buckets. You can have a population of t-shirts. So that's what I mean. Most things we don't know the population. So you take a sample and calculate the sample standard deviation, and you can use that. The moment you start calculating the sample standard deviation, you are inching towards not the Z world, but the T world. So you are now inching towards a distribution known as T distribution. Of course, you can approximate that towards the Z. In your hypothesis testing, you will deal with degrees of freedom. In fact, I've explained it all here. Simple. Degrees of freedom is basically that gap, okay? The number of independent pieces of information that went into computing the estimate. And you can look at it with this example, suppose that there are 10 observations and we have an estimate of the sum of 10 observations. Now, if 9 out of the 10 observations are known to us, but the 10th one cannot be known, you can find the 10th one by subtracting the sum of the 9 observations from the estimate of the sum of all of the observations. This way, if the 9 of the observations are known, of course, they must be known. If they are, then the one left, becomes redundant, becomes superfluous, useless. So we say that the degrees of freedom for the estimate will be the sum of 10 minus 1, making it 9. So I want you to understand that the degrees of freedom becomes useful once you collect a sample. Once you collect a sample, because the sample is a mimic of the population, because the sample is a representation of the population, there is a modicum of something you didn't collect. And that's something you didn't collect. Well, we are allowing you that degree of freedom to operate, and so you don't want to take it lightly. We are going to look at one sample hypothesis testing, and then we'll check whether we should use Z or T. Well, for your information, you know it by now, that we use Z when the sample size is large, and we use T when the sample size is small. What do you mean by large? Large is generally seen as anything bigger than 30, or anything 30 or more. Small is anything less than 30. T is used mostly when the sample is small. Z is used when the sample is large. But I'll show you something. Before we proceed, I want you to remember and run all of these packages. These are all pandas, NumPy, Matplot, Seaborn, SciPy, StatsModel, everything that you need. You have this. I want you to run this whole thing. Okay. This shows that it's running. It's running. When the star is gone, it means that the running is done. This thing has delayed. Normally, it's not supposed to delay like this. I don't like this. I don't like this. Okay, it's done. So you're going to calculate a one sample, okay? We are going to use Z, and I'm going to ask you, why are we using Z? Well, we are going to use Z under the assumption that the population standard deviation is known. Wow. So if it is known, you got to use Z. The standard deviation is known. Now we're going to calculate the standard deviation as well for you to see. So let's remind ourselves small. Do you remember the Brukutu data set? Now, I've put a statement here that it is hardly the case that you know the population standard deviation and not the mean. But we're going to assume that. We're going to assume that we know the population standard deviation. So suppose we have a sample, and if you can remember the quantity demanded of gene bitters, we have that from the Brukutu shocks, only the quantity demanded of gene bitters. In fact, guys, in case you have forgotten that data set, let's see if I can show you quickly. Where is that? Oh, you had that data set, right? Because I think I shared it somewhere. There you go. Okay. So you have it in your listing. So this was a data set that we had last time we met. And this column is what we are going to do. We are going to check the quantity demanded of Brukutu gene bitters are here. These are all the quantity demanded from 1 all the way to 40. From 1 all the way to 40. Okay. So that's the quantity demanded of Brukutu gene bitters. The question is this. Look at the question. Question says, suppose we have that sample. You want to test if the mean is significantly different from the national average of 160 bottles of gene bitters. So there is a certain hypothesized mean for the nation, which is like the population, the mu naught. You want to check whether your mean, now right now we don't know the mean, we're going to calculate the mean. You want to check whether your mean is equal or statistically different from the national average of 160. So the national average of 160 means that the national average of Akpoteshi, that is taken every single time, is 160. Use your computed information to check whether there is enough statistical evidence. In other words, do you have statistical macho to conclude that your mean that you're about to find, your mean is statistically significantly different from the national average of 160? Is it significantly far away from it? And we have to use the alpha level of 0.05%. In other words, you are allowed a modicum of 5% error. You can make up to 5% error, no more. You are allowed. Remember, the alpha is the expected error. So what's the first thing you got to do? You got to formulate the null and alternative hypothesis. Guys, I've kept here empty. Who can formulate the null and alternative hypothesis for us? Remember, we just did an example right here. Okay. We just did an example here. Who can formulate the null and alternative hypothesis? Now remember, the one that we have is here. This guy. Yeah. Okay. So who can formulate the null and alternative hypothesis? You're looking at the sentence, is what is going to be the symbol? What symbol are we dealing with here? It's right in front of you. What symbol? It says that you want to test the hypothesis that the average is significantly different from the national average of 160. What symbol are we dealing with? What symbol?
I think it's equal to.
Equal to, that's it. Okay, so the symbol is equal to, so you're going to use the equal to 160. Remember, 160 bottles. So I'm going to just change this number and write 160 here. Okay. And of course, because the equal to sign will take the mean, the null, and then the other one will take the alternative. So you have this as the equal to, then it is bottles. So let's put bottles here. And then the alternative is going to be the not equal to. And then check the results. So there you go. Oh, I didn't put it there. I'm supposed to have the mu here. Okay, so you have the mu, okay, equal to 160 bottles. And then you have the, oh, come on. 160 bottles, and then you have the alternative equal to not equal to 160 bottles. So you've been able to formulate the null and alternative hypothesis. Oh, by the way, you will always have to formulate this null and alternative hypothesis. Always, always, always. So that's why I'm going through most of them. Now you're done with the first step. Now, which test do you use? Well, we've been made to make some assumptions. Okay, the samples are drawn from a normal distribution. Now we need to check the sample size. If the sample size is more than 30, then we know that we are going to use Z. If you can remember, our own is 40. Okay? So when it is like that, the central limit theorem states that the distribution of the means will be normally distributed. But is that really the case? Is that really the case, for example? We are going to check the distribution of the mean. Now, if the sample is less than 30, we would have been able to apply the Z test. Okay? If, and this is a point, this is a very important point because a lot of people just pick this thing and they don't know. If and only if we knew the population distribution was normal. Now, right now, we don't know whether the population distribution is normal or not unless we test it. We could also verify that with a t-test. Okay, so what we are going to do right now, we're going to do both the z and the t, and then we'll select the one. But right now, I know the one. I know the one that you got to choose. But I want you to know when to use which one. Now, for the z, you use it when the sample size is large. That is more than 30. This one is large, more than 30. But the question is the distribution normal? We need to check the distribution. The next point is that observations must be from a simple random sample. We initially know that a sample here was collected, so simple random sample has been understood. Is the standard deviation known? Well, in our case, yes. So first thing we are going to do is to find the mean and the standard deviation. So I've left that gap here for you. Can you find the mean and the standard deviation? Can you find it? Okay, so there's a way to find it. Remember the name of the data set was what? DF. So we are going to type DF. This has to be, what I'm typing here has to be code, not markdown. So I need to be sure that it's in code. Okay, DF, then you do this square bracket, and then you put the name of the kill that we are looking for. Okay, so you do one apostrophe, then put kill in the apostrophe. So we are picking kill, which is inside the data set, and then do a dot for the mean and type mean. Okay, and then put a bracket. That will find you the mean. Bring a comma. You also need to find the standard deviation. So I'm going to copy the same thing, post it here. Okay, and then just change the mean to what? Standard deviation. And standard deviation is written as STD. It's not sexually transmitted disease. STD is standard deviation. So that's it. This should run and it should give you the mean. Let's do that and see. Have we loaded the data? Okay, it won't work because I've not loaded the data. So let's be sure that we've loaded the data here. So let's use this command. This command should load the data. Good, data is loaded. So now let's go down and then run this again. We should not get to this error. There you go. So now we can find that the mean is what? 175. And if you can remember, that's what we had the last time. And the standard deviation is 29.78. So we know the mean now, the sample mean is 175. The sample standard deviation, because we deduced that, we're not given. Okay. But we are still going to use what? We're going to use the Z. Why? Because the sample is large, but we also know the standard deviation. In fact, in this case, even when you use the T, it will lead to the same conclusion as the Z. Let's look at it. So this is a command. Okay? This is a command. We're going to perform our one sample Z. And when you look at it, these typos should not be made. No typo is supposed to be made. You write Z start, P value, Z test, then you take the quantity demanded, which is inside the data set DF. The hypothesized mean was 160. Remember, we're told that the national average is 160. So that's a hypothesized value. That's the one you use to formulate the null hypothesis. And all of these are my own typings. So we print and say that Z statistic, and that will give us the Z statistic. Then we also checked the p-value. Remember, you always want the p-value to be less than the alpha, which is the level of significance. Alpha was given as 5%. We are going to check the p-value against it. And then here, I've also printed the mean again, so that we remember the mean. So this is your result. I just run this whole command. And you can see that the Z statistic is 3.19, correct to 2 decimal places. The p-value is 0.001. It's not 10%. Okay, it's not even 1%. It's 0.1% or 0.14%. Okay, so it's way less than 5%. Okay, so our conclusion would be that since the p-value is less than the 5% significance level, it means we have enough gravitas to reject the null hypothesis. What did the null say? Go back. Look at what the null said. The null says that the mean is the same as the national average. The national average is 160. Now we are rejecting the null hypothesis and conclude that the mean is the mean bottle, the quantity demanded of the bottles from these shops are significantly different. So we go for the alternative. They are significantly different from that of the national average. Statistically speaking, at a 5% level of significance, okay, there is even a 0.01% level of significance. That is, the error we made was so tiny. It's way, way, way below 5%. And with that error, with that tiny error, we have enough confidence to reject the null hypothesis. We have enough gravitas to reject the null hypothesis in there. That is it. What if we had performed a one sample t-test instead of a z? Okay. What if we had done that? Well, we already know that if I decided to just bring this command here, not because that is exactly what we got to do, but it's because if you ever need to do the t-test, which I'll give you, if you ever need to do the t-test, then you also know that this is how you write it. Watch it. That one to you write t-test here, but you bring p-value, and then you do, sorry, these are my own writing. Write t-test here, p-value, then you write stats.tt-test underscore one sample. And then you write the name of the variable in question. And the population mean is rather written as pop mean. Okay. I'm using the stats command. And that is all you got to do. The rest is just my own write-up. So when we run the T, now look at the results we had. This is interesting. I told you that it is likely to approximate that of the Z. So this is a T approximation of the Z distribution. Why? Because the sample is large. So even if you use T, because the sample is already large, it will be closer to the what? To the Z, because Z is for large sample. That is why both of them have got the same test statistic, 3.18. That is also why both of them have got almost the same p-value. But at least this is to guide you to know that we have the Z, as well as the T. This is how you calculate it. In both cases, you're going to reject the null hypothesis. Okay. So the interpretation, I've left it here for you to write. Okay. You should be able to write the interpretation very, very, very nicely. You will say that the p-value is the p-value, which is 0.014%, is less than the alpha level of 5%. That is the significance level of 5%. And the mean quantity demanded is then concluded to be statistically different from the hypothesized mean of 160. The national average bottle is 160. Okay? Because our sample mean is 175, if you can remember. And this is greater than 160. So it means that if the national average, they are on average collecting 160 bottles, your 40 shops is collecting more bottles. The difference is 15, but that 15 is not a mere difference, it's not by chance. This difference of 15 is not by chance. It is statistically significant. And that is what you want to see. So you are going to reject the null hypothesis and conclude that the mean, the mean bottles of this quantity demanded of bottles here exceed that of the national average. That's what you should put there. Now, if this one column kill the quantity demanded, if it was ordinal, this is very important, guys. If this was ordinal data or even continuous data, like ordinal or like rank, okay, ranking. But if they are still not necessarily normally distributed, or in other words, if they are skewed, you will not use the T, you will not use the Z. If the data set is skewed to the right or to the left, it means that it's not normally distributed. And if it's not normally distributed, TZ don't work. So you need to get to the number.
Research methods.
People who don't normally pay attention, that's what happens. In fact, let me just okay, I've enabled waiting so that people Do not enter by heart. All right. So, what was I even saying? What was I saying? If the mean, if we have an ordinal data, instead of a skewed data, instead of a normally distributed data, you cannot use the T, you cannot use the Z. You got to use the non-parametric. Remember, the T or Z are for parametric data. Write it down. Meaning they are for normally distributed data. That's what it means. They are for normally distributed data. But when the data is non-parametric, non-normally distributed, that is skewed to the left or right, in that case, you don't check the mean, you check the median. And so this one sample test, we got to rather use the one sample sign test, which actually tests for the median. We got to use the one sample sign test instead of what? Using what we just used. I have a whole story of a question for this purpose. That's why I'm digging into. Now, this one sample sign test is also called one sample Wilcoxon sign rank test. It's the same thing, one sample Wilcoxon sign rank test. Now, first, we got to check whether our Q is truly normally distributed or is not normally distributed. Because we said, what if it's not? So let's go and check it. How do you check it? Use a test known as Shapiro test. There are several tests, Pomogoros, Menos, several tests, Anderson, Darling, and so many of them. Just let's focus on a simple one, Shapiro test. So we're going to use the Shapiro test to check whether the data is normal. I've created a command here for that purpose. So I've created a statistic with a p-value, and I've indicated I check whether this Q, which is a quantity demanded of Jembe test, using the Shapiro, check whether it is normally distributed. I've given a definition here that if the p-value is greater than 5%, oh, by the way, for normally distributed, okay, you can see it even here. If the p-value is bigger than 5%, that is 0.05, then it means the data is normal. And that is how it is. So that one is kind of opposite to what we normally know in normality. It's normally opposite. Normally for all tests, most of the tests, when you rather want the p-value to be what? Smaller. Okay. But this one, you want the p-value to be bigger for normality purpose. If the p-value is less than, that is why I have else. In other words, if it is not greater than 5%, but it's rather less or equal to 5%, then the data is not what? Normal. So we are going to run this and check the p-value. Okay, and I've created a result to indicate that check. Let's run it and see. There you go. So you can see that the p-value is what? 91%. Which means the data is not normally, the data is not normally distributed at all. Okay, for the what do you call it? We said if the p-value is greater than 5%. Why did I say this? It's supposed to be normal, right? Yes, it's supposed to be. Yes, Ramatu.
Yeah, so I was about to ask that question. So it's fine now.
Which question?
Concerning the test, the condition you are setting for the Shapiro.
Let me edit it. Yeah. There you go. Sorted?
Yes.
Yeah. There's a command. Okay. So you have that. In fact, you will later see, if you guys can remember, do you remember last time when we checked for the kill, it even had two mode. Do you remember? It had two mode in the kernel density plot. One mode was on the left, one mode was on the right. And we looked at the thing. The thing doesn't even look normal at all. And in fact, you can check for the normality graphically. And you see that it's not normal. And this is it. So that was a typo, by the way. So it's not normally distributed. It's not normally distributed. So whatever thing that we use, the one sample t-test, guys, that we just used, it was not supposed to be used. That's the point. It wasn't supposed to be used. So it means that we got to use what? A non-parametric test. What non-parametric test can be used? We indicated that we got to use one sample or Wilcoxon sign rank test. So that's what we're going to use. What is that? Well, the one sample is a non-parametric analog of the one sample t-test. It takes the difference between each element and the hypothesized value. It subtracts the 160 that we had, the national one, from every number. So if you go to all the 40 observations, it will take 160 from it, 160 from it, okay? Testing if the median of the sample is truly different from 160. Not when the mean, no, the median. The test statistic is the sum of the positive ranks, okay? And it's based on the sum of the sign ranks. Okay, so let's run that and see. So from the SciPy statistics, I import this called Wilcoxon. The statistic is written, the p-value is given by Wilcoxon, our data is the Q, and we can see that we are subtracting the 160 from the Q. So every Q, you can subtract 160 from it, and then you can print the result. Let's do that and see. In fact, I can also do you have Francis Dankwa in your class? Can somebody just confirm whether you have Francis Dankwa in your class?
No, sir.
Can you all confirm if you have Francis Dankwa in your class?
No, sir.
No, sir. Francis Dankwa in our class.
Nobody knows Francis Dankwa.
Emily is not in our class.
Sorry?
There was another person, Emily.
Oh, don't worry.
He just, I don't know.
She just left.
No problem. All right. So let's run that.
I'm still here.
Emily is someone I work with. Oh, Emily is a lecturer. So.
Oh, okay, okay.
He's a mathematician with multiple universities.
Oh, I see.
So Francis, let me say Francis. We focus on Wilcoxon. Wilcoxon sign rank test. You can see that the one sample Wilcoxon test is 94. The p-value is what? 0. Basically, what does that tell you? It tells you that indeed there is a significant difference. So the test that ideally we should have used is that. So anytime you are doing a one sample, the first sensible thing to do is to check for the normality. That's it. Check for the normality, and see whether the data is what? Normally distributed. Normally distributed. And if it is, okay, if it is, then you can use the T. If it is not, then you can use the, what do you call it? The non-parametric equivalent. In this case, which is the Wilcoxon. That's how it works. Very good. That's one sample, Opele. That is one sample. Let's go to two sample. Two sample is an interesting area. Two sample is when there's, for example, there are several applications of two sample. Look at them. If you want to compare the difference in treatment, let's say that somebody says that he's created a new AstraZeneca, or somebody even says that he's created a new drug that can be used to cure every cancer. Guys, what do you think? Will people rush for it or they will not rush for it? They'll rush for it. But before we can actually know whether that drug is potent, we need to check it against a placebo. Okay? What is a placebo? I know that you might say that it's like a sugar pill and things like that. Well, I have even a bigger definition for a placebo.
So a placebo is a state of mind.
Yes.
That allows you to assume anything that you want to be and become that thing.
Exactly. It's not a drug alone per se. For example, the aura of professionalism beseeching the medical doctor, who is usually garbed in a white overall with a stethoscope around his neck, that aura is said to have a cathartic ventilation effect on the patient. Just like the psychic paraphernalia in the voodoo shrine can have a cathartic ventilation effect on the person going to see the voodooist. So that is the same thing. When you enter a voodoo shrine and you see that that man has economics books, business analytics books, marketing books, you ask yourself whether this person really is a problem. Like your faith in that person is dissolved. You want to see bones and human head and human skulls and things like that. Then you can have beliefs. So go to your kuni panama or town for no dinner wama. But and that is catharsis. A placebo is a psychological impact. Okay, that catharsis you have on you by virtue of anything. But there's another thing called nocebo. You guys should look for it. Nocebo is when you have a negative effect on yourself, that something is negatively going to happen, and it actually happens to you. Because you believe it's going to happen, you act and behave and program yourself in the direction of your most dominant thought. You release dopamine, oxytocin, serotonin, endorphin, and your body reacts in the direction of your most dominant thinking. As a man thinkers, so he is. The same energy it takes you to pass an exam is the same energy it takes you to fail an exam. You're a vibrational being. You vibrate at your frequency. Thoughts are things. Your subconscious mind doesn't take anything for a joke. That is why it's always important to be positive-minded. Even if you can't do it, you tell yourself, I have done it. Even if you can't win, you say, I'm a winner. I'm a winner. I'm a winner. I used to do that. I had a 3.97 GPA. Okay. In mathematics and economics, and people said that juju, it's not juju. Your mind is the most unexplored continent in the universe. That's for another day. Let's go to real life application of two samples. So you can assess, two samples can be used for several things. You can look at the effect of a new surgery on a patient. So if you come out with a disease, a potent drug, nobody will believe it until you've used that drug on people, and then you've used this different people to give them that same thing, but this time a placebo. A placebo. And then if those same people also say that they have won, I mean, their cancer is gone, then you know that it wasn't your drug that actually made them well. They had a cathartic ventilation impact on them. That led to that. Two samples can test that. Two samples can be used to assess the performance differences between groups. Let's say you want to check whether foreign banks outperform domestic banks. Is that true? You can use a two-sample test. You can analyze the differences in attitude between different age groups. You can compare the levels of pollutants in different locations, determine if sales differ between two branches, determine if sales actually happen in different countries, evaluate the impact of a new marketing campaign on performance of sales. In fact, you can even look at the effects of interventions. And there are several two-sample tests. For example, the common one that we know of is the two-sample t-test, the t-test, two-sample t-test. That one, you compare the means of two independent samples. Please note, the samples can be dependent or independent. Samples can be dependent or independent. Dependent samples are before and after samples. Dependent samples are where the subject is the same, but that subject is treated differently. So suppose I do you business analytics supervised learning, and then I record your scores, and then I do unsupervised learning, and I record the scores again. The same subject is what I'm using, but the scores are different. Such a sample is dependent sample because the subject is the same, but the samples are different. But then suppose I take the male alone, I give them supervised learning, and then I take the females and I give them supervised learning, and I compare the males and the females. The samples are the same. Sorry, the samples are different, but also the subjects are different. So that's the difference between dependent. Dependent means paired, matched. Independent means unpaired, unmatched. So T-test, both of them are T-test and Welsh test, both of them are independent. But the difference is that T-test looks at equal variances and the Welsh looks at unequal variances. That's the key. That is the main thing. Otherwise, they are all TT. Their non-parametric analog are known as Mann-Whitney U-test. That is a non-parametric analog of the T-test. Sometimes it's also called Wilcoxon rank sum test. Take note. This one, I've created a table here, but it's also called Wilcoxon rank sum test. It's different from the Wilcoxon signed rank test. Remember, the T-test has got a paired version. Paired. I didn't bring that paired here. But that paired, its non-parametric analog is the Wilcoxon signed rank. So it's a non-parametric paired T-test. Get the differences between all of these tests. It will help you. Let's take an example. Before undertaking a two-sample test, okay, we are going to plot the volume across locations. You see, the locations are rural and urban. If you can remember, rural and urban. So I'm going to check something here. Test though. I'm going to test right now whether the quantity demanded between the urban and the rural, which of them actually take a lot of acquisition. That's what we are trying to check. Graph can give us a bit, but test will tell us more. So let's plot it first. Because after we have plotted, see, the plotting is a good start to see how everything looks like. So when we have plotted, it gives us a feel of the whole thing. Now, I know you guys have the plot. You have it somewhere up there because we did it during visualizations and charts. So I'm just going to copy it here, okay, and then put the point here. I'm just going to copy it here. So I'm going to copy it here and then run it. And then we check to see. I will also show you all the other variables, just so in case you've forgotten the other variable, so you know. So let me just look at it here. So this is a plot. The key point there, this one will give you the size of the plot. This is actual volume. I have LOC for location. I've indicated certain things for it to even show you the quartiles, okay, the first and second and third quartiles. Okay? And I've shown some red colors to pinpoint this. All the rest are just here. Let me run this. Okay. There you go. So these are the two. So at the bottom here, we have urban, and on the section here, we have rural. Just by looking at the graph, which one would you say the quantity demanded? Look at the y-axis. And then, by the way, we are looking at the mean. Which one would you say that the quantity demanded, that's the average of the quantity demanded, is more? Is it for the urban or rural?
Urban.
Exactly. Exactly, for the urban. And in fact, you should note that the median, I mean, we could add the median here. You can even intersect the box plot. So that will give you the median of it. But here, you have the mean rather. Okay, which is, if you look at it, the mean is a little around 199, something. But in order to know it, these are the variables, by the way, in case you've forgotten the variables of the data set. These are the variables. But the graph can give us a picturesque understanding of the whole thing before we start. And from what you are saying, it is not true that the villagers, the rural dwellers, actually drink a lot of apio or akpetish. From this graph, it appears that the city dwellers, the urban dwellers, are consuming a lot of gin bitters. But that is graphical. Let's see statistically. So let's look at some summary statistics first. Okay, I'm going to calculate the summary. So this will show you the mean and then some few things. Okay. Now this last command here, I've dropped any missing values. If there are missing values, this command will drop it. But for this data, if you can remember, there were no missing values. So I'm going to show you the mean and the standard deviation for both the urban and the rural, the quantity demanded. Okay, so I have this here for you to fill in yours. Now, if you check it carefully, I have this command, But you see, when I run it and it tells me that there's an error, I check the error and I realize that I need to do for the urban. So I'm just going to change this one and then change the rural to urban for each one of them. Okay. This is supposed to be for urban. And now I can run it. And there you go. So you can see from the result that the mean for the rural is 154. And then the mean for the urban is 196. So you can see that the urban is consuming a lot of akpeteshie than the rural. But the question is that significant? That's all we want to know. Now look at their standard deviations are almost the same. The sample sizes for two of them are almost the same. This is sort of a equal variances. That's what you see there. Okay. Now, but we are first going to run the unequal variances. Okay, we are going to run the unequal variances first so that you know how that one is done. So I'm going to do the test here after invoking SciPy. Use this one, run for the rural and urban. I'm assuming equal variances are false. So I'm doing unequal variances. So equal variances are false. And then I'll run the thing. It is going to give me the Welsh t-test. Let's show the result. You can see that the Welsh t-test means that you have a -6. -6, the negative doesn't matter because this is a normally distributed angle. Whatever is on the right-hand side is on the left-hand side as a mirror image. That is a negativity. So we normally focus on the absolute value. But look more at the p-value. Look at the last version of the p-value. It is E minus 0.7. This means that there are 7 zeros before the 2, 3. The E minus 0.7 here means there are 7 zeros before the 2, 3. So that means you have 0.00006023. So that means that the p-value is what? 0. What does that mean? If the p-value is 0, it means we made no error, which means that the differences that you saw are not just mere chance. The differences are statistically significant. So the urban dwellers are statistically alcoholic consumers than the rural folks, as far as the quantity demanded of generators is concerned. Now, I decided to even do the equal variances, which is a real deal. This is known as two-sample t-test. Sometimes it's called student t-test. Let's run that. Now, remember that this one, the difference between this one and the previous one is that this one, the student test, uses pooled standard deviation. So instead of using the standard deviation separately, instead of using 20/20 separately, it uses 40 for both of them when estimating the standard error of the differences. That means that it's assuming something we call homoscedasticity, unlike the previous one. So they are all the same variances. Okay, so let's run that. When you run that, remember, you can see that here, instead of equal variances was false, like the previous one. This time, the equal variances is what? Is true. That's the only difference. That's the only difference. You run that. Let's run that and see the result. So this time, we have equal variances. Again, look at what is happening. The same answers. If I check the answers, and you see that the same thing. Watch the p-value. At the end is E minus 0.7. Okay, that is an exponent. The same thing. Okay. Look at the t-statistic. Okay. The same thing, just that when you're going further, it changes slightly. After the 286, okay, even that, 785, it still goes. Okay, it still goes. I think it is 964. And then this one is 963 at the end, but almost the same thing. Okay. So either test here is telling you that there's a significant difference between the alcoholic consumption of rural and urban dwellers. All tests are proving that. And guys, if you're writing your thesis, your anything research, and then you prove statistically like this, your gravitas is high. That's it. You have enough gravitas. So in essence, if you are not sure, so I've concluded here that if you are not sure whether the variances are equal, which one should you use? Is it the Welsh or the student t-test? If you are not sure, or if the sample size differs significantly, in our case, they are the same, then Welsh is the one to use. In fact, most people don't even go through which one to use. They just use the Welsh. Welsh is generally preferred choice. Okay, why? Because it's more robust to violations of the equal variance assumption. The standard t-test should only be used, only if the equal variance assumption is reasonably met and the sample sizes are relatively similar. In our case, the sample sizes are relatively similar, as you can see. We didn't really test for the homoscedasticity assumption, but you can test it and you'll see that in this case, the student t-test suffice. But again, the other one to lead to the same conclusion. So normally when you do both, it's great. Then you tell the reader, the examiner that, look, I did both of them. I got the same result. All these things are assuming that the quantity demanded between the two are normally distributed. Now, do you remember the graph for the kernel density plot for the two? They were similar, but they seem to have a bit of multimodality, if you can remember. Like they were not smooth bell shape. They go up a little bit, come small down, and then go up properly. So you can test whether it's normally distributed between the two. And then if so, you rather use the Mann-Whitney U-test. The Mann-Whitney U-test is also called Wilcoxon signed rank test. Now, please note, this is a non-parametric analog of whatever we have done. This is just assuming that the data is not normal. That's all, nothing more, nothing. So if you check and the data is not normal, then you can look at that. So watch some key important points here. Watch it. Most of the statistical tests are optimal under various assumptions, like if you check it, you have independence, homoscedasticity, or normality. But it might not always be possible to guarantee that the data is normally distributed. That is why we have non-parametric tests. They are statistical methods that don't need a normality assumption. And then the distribution of the normality, they don't need it. So non-parametric methods are good. So first, you got to check if the distribution of the two samples are equal or are not equal. Okay, and if so, you do that. These are for skew data. When the samples are usually small, when they are usually ordinal or ranked, okay, the dependent variable are usually ordinal or ranked, like quantity demand. They are usually ordinal or ranked. And then when the independent variables could be categorical, in our case, they are categorical. You can use the Mann-Whitney or the Wilcoxon rank sum. Please note that the Wilcoxon rank sum is not the same as a Wilcoxon signed rank. Signed rank is when the data is paired. In our case, the good thing about our case is that our data is not paired. It's not paired. But because they are all 2020, we can assume that they are paired and they use that just to demonstrate a point. Anyway, so this is a Wilcoxon rank sum, also called Mann-Whitney. I did that and just check something. It's beautiful. The Mann-Whitney U-test. Oh, by the way, the test statistic there is called U-statistic. U-statistic. Normally you have U1 and U2, then you take the lower one. This is a U-statistic. And the p-value, look at the p-value. The p-value tells you that it is almost zero. So again, no error. What does that mean? The fact that the p-value is almost zero means that you didn't make any error. You didn't make any mistake, which means that there is a statistically significant difference to prove that the means. In fact, in this case, it's not even the mean, it's the median. Let's check. Median. Median. Sorry, let me write median. So you can see that the medians are not the same as the means. So the median for the what do you call it? The median for the RUA, the quantity demanded for the RUA, the median for them is smaller than that of the mean. is smaller for that of the urban. So the urban are still consuming a lot of alcoholic beverages. Okay, you can see that right here. The urbans are consuming a lot of alcoholic beverages. They are consuming 200, whereas the rural are consuming 150 on median terms. What did I do? Okay, so that's it. If you look at the standard deviation, as for that, we know that they're the same. The sample sizes are the same. So that is it. So this clearly shows that there's a significant difference. That's all. That's basically. So again, we reject the null of no difference. The null says there is no difference. That's a lie. We reject it. Okay. And conclude that, quantity demanded in the urban section is significantly outperforming the quantity demanded of the rural folks. That's what it means. Guys, do you know anybody called Atelu Geoffrey? You know anybody called Atelu Geoffrey?
No, sir.
Fine. Let's move on. So urban people significantly consume a lot of akpeteshie than rural folks. Okay, I put there more consumers of akpeteshie are in the urban centers. So that is how it is. Now, this is under the condition that we indicated. Now, in a Wilcoxon signed rank, we are assuming that the data is paired. Please note that if the data is not paired, you cannot use this. In our case, they are not paired, but because the samples are the same, I had to use a code to create the pairedness. When you use this, I've told you an example. Suppose you look at only women, their situation, pregnant women. Before the first trimester, you check maybe their pressure. Then this same pregnant women, in their third trimester, you test their pressure again and you record it. And you want to check whether this pressure level of the same subject is a different, statistically significant different from the previous one. Then you can use this very one. That is exactly how it works. That is exactly how it works. Do you know anybody called Ramatu Ama?
Yes, sir.
Oh, okay. These are latecomers. Okay.
No, sir, I'm here already. I'm connecting my laptop, please.
You should have told us. You should have told.
Sorry, sir. Sorry.
I see everybody leaving and coming. All right, so let's move on. So that is it for per data set. And I've said it multiple times. Let's say that you have a test score of 10 students before and after attending a tutorial. You want to test whether the tutorial is significant in changing their scores. Like, does this tutorial help them in getting a better score? You can use Wilcoxon signed rank. Signed rank. I have to do the same thing for signed rank. So here, I did a signed rank test here, and I ran the result. And this is a result. Again, look at it. But I can change these values because they are looking at the medians. Okay. So remember, these non-parametric tests, they don't look at means. They're looking at medians. Okay. They're looking at medians. So when you're running, you ensure that you're dealing with what? Medians. So what do you see here? Median is 150, this is 200. And again, paired is indicating that there is the p-value is 0. So since the p-value is 0, we reject the null hypothesis once again. Okay. Confirming indeed that these guys who are in the urban centers are still consuming a lot of akpeteshie. Not small, but a lot of akpeteshie. Now, there's something you can see here. The test statistic is 0. What does that mean? In fact, I've asked this thing in an exam before, so it's important here. For this very example, the Wilcoxon signed rank test did not give us an actual value. Look at the Mann-Whitney. Mann-Whitney gave us 32, but the Wilcoxon has given us 0. What does that mean? it means that all the differences go in one direction. Very, very strong signal. Strong signal of differences. You know, is the most extreme possible result one can get. So there is no variation in the direction of the differences. Okay. And I've given you an example that, let's say you're comparing satisfaction before and after an intervention, and for every participant, satisfaction has increased. So for everyone, the satisfaction has increased. It might look like there is no difference since everyone's satisfaction has increased. The test statistic will be 0. The p-value will be very, very small. Okay? And you can see that the p-value is small in our case. So we'll conclude that the intervention has had a significant positive effect. In other words, there's a huge difference. That's it. That's why. So sometimes some people say that it's my distance wrong. It's not wrong. It is what it is. All of these things that we've done, guys, they are wonderful. They are super. They are superlative. The problem is that they are checking the mean or the median. The mean or the median. That is a measure of central tendency. That is center. It's not checking the distribution. So we need a test that will look at the entire distribution of the data set. Which test can look at the entire distribution? One of the tests is known as Kolmogorov-Smirnov test. Unlike other tests that might focus on specific parameters like mean and median, the KS examines differences in the entire shape, the distribution, the center, the shape, the size, everything. Okay? And that's why it's sensitive to the deviations in the shape and the location of the distribution. When you want to do exploratory data analysis, it can help you. Okay. You can use it to check if the sample comes from a normal distribution. You can use it to check if the two sample distributions are likely from the same population. You can use it to check the consistency of models. So let's say you have model 1, model 2. Emily, that reminds me, you got to use it to check one of our models. Okay. To check whether the CRS or the VRS model, are from the same distribution. And for those who are doing machine learning, you can check whether a particular model, whether it's random forest or you are dealing with T-distributed neighbor, stochastic neighbor, any, OLS regression, elastic net, ridge regression, lasso regression, decision trees, anything. When you are checking the efficacy of models, you can use Kolmogorov-Smirnov test. You can use it for several things. But it has an issue. Okay? It's typically designed for continuous distributions, not static distribution, not binomial distribution, but for continuous. Okay? And it can also be sensitive to deviations from the center, like we've said. Anyway, I decided to still show you how the Kolmogorov-Smirnov test is for this very example. Remember, we are looking at the entire distribution, everything, the mean, the deviation, the skewness, the kurtosis, everything. And this is a test for rural and urban. Okay? And look at it. KS test is 0.6. The p-value is that. So you see, even though the p-value was very, very zero, this one, it is shown clearly that, yes, it's still zero, but the zeros are not too much. Okay, like that, because it's taking everything into consideration. But again, there is a significant differences in the quantity demanded between urban and rural. Okay, so look at the conclusion here. As the p-value is 0, is less than 5%, not only are the averages statistically different, the means are statistically different, the medians are statistically different. Guys, this is a good test. The shapes, not only the measure of central tendency, not only that, the shape of the distributions, they also differ significantly, which is providing a statistical torturing, okay, a strong gravitas that the distribution of quantity demanded for both rural and urban groups are statistically different. And that means that location, which is a center, spread, which is a deviation, and the overall shape, which is a kurtosis, okay, of the distribution, they differ significantly. Not one thing, but everything. And that that could imply structural differences in how quantity demanded behaves, okay, across these particular groups. So the Kolmogorov scenarios can be used as a test to justify the distribution. Emily, that should remind you of the Semmer-Zellenyuk adapted Lie test. It's a very so it's one thing we can use to confirm the Semmer-Zellenyuk adapted Lie test, to check for the distribution of the entire location, the spread, and the overall shape of the distribution. It's a good test. It's a good test. All right, ladies and gentlemen, that is 2 samples. I want you to learn 3 samples on your own, given the beautiful slide and tabular analysis that I've given you. 3 or more samples. Okay, there are quite a number of them, and they are split into parametric and non-parametric. What is the difference? Well, the parametric test, we have one-way ANOVA, two-way ANOVA, and MANOVA and ANCOVA. Find the difference. ANOVA is when you have 3 or more. Remember, we looked at 1 and 2. But ANOVA is when you have 3 or more samples. Guys, mathematics are powerful in these areas, but I didn't bring any of them. In fact, throughout everything we've done, the test statistics for all the things we've done, you can write the mathematics for them, but there's no need. Just understand the principles we've done. So 3 or more samples, you can use ANOVA. One way. Two way is when the independent variables are 2. One way is when the independent variables are 1. Okay, numbers. And then you can have repeated ANOVA. Remember, the repeated ANOVA is like the paired, the matched. Okay, that is when the sample. So you check the first trimester of the same woman, the second trimester of the same woman, the third trimester of the same woman. And now the samples are 3. That is when you use repeated ANOVA. They are all parametric. But the non-parametric version of the repeated ANOVA, that is the name, it's called Friedman test. The Friedman test. And then the non-parametric analog of the one-way ANOVA, the one that is not repeated, is Kruskal-Wallis test. Kruskal-Wallis test. Okay. You can use these tests in most of your work. There's also the Moods median test. It tells you the medians. Okay. You see, these ones are looking also at continuous variable, but you can use this one. It's a kind of equivalent to the first one, the Kruskal-Wallis test. And then another equivalent to the Friedman is a Quaid test. Very, very less common. Okay. What it does is that it adjusts for the covariation in the non-parametric setting. And you can use it for that. Learn at least the one-way ANOVA. Learn how to do the one-way ANOVA in Python. I want to repeat. Learn how to do the one-way ANOVA in Python and look at the results and understand the interpretation. Now, when do you use these tests? Okay, when do you use them? Well, we've said it. When they are independent samples is when the samples are separate. The subject is separate. And the related samples are the same as the paired. The related is when the subjects are not separate. They are the same subject that you are repeating. That is when to use those things. And of course, their non-parametric analogs are the ones below. The most popular, important ones of all these are these 4. The parametric 2 and the non-parametric 2. Now, let me give you a bonus final thing. Yes, Ramatu.
Yes, sir. So I want to ask, under the non-parametric, I want to know where would the chi-square fall?
The chi-square test for independent doesn't look at these. They are still tests of it's a test for independence. So when you want to check whether a particular group is independent of another group, you will still classify them as 3 or more sample analysis, but it is not comparing it's not comparing the means or the median. It's for categorical testing.
Okay, sir.
It's used more for the categorical testing. And yes, I didn't add that here, but you can still include that as because it's a test for independence. We have a test for it to determine that a particular group is independent of another group. Now look at these bonuses. So the people that will use that one you are talking about mostly, the people that use are the HR4. Okay. Those that do more with not hardcore quantity related, but that is not to say it's not good. It's still powerful, for such purposes. Now, one last thing before we close. You see these ones? All these are looking at 3 or more samples. So it will tell you that there's a statistically significant difference across the groups. So let's say that you look at state banks, domestic banks, private domestic, and then you look at foreign banks, and then you try and look at their profitability. And you want to check whether there's a difference in the profit of each one of them. And then you realize that there's a difference. The test will tell you that there's a statistically significant difference in the profit across all these. But it doesn't tell you which one is driving the difference. Is the difference in all these 4 or 5 or 6 or 10? Is the difference being driven by only foreign? Is it different? For example, there are so many master's degrees. You can say that there's a statistically significant difference in the scores obtained by the MSc sandwich, MSc regular, MA, okay, BS, MPhil, MBA, EMBA, weekend MBA. They are all master's degree. And then you find that there's a significant difference. But you want to know who is driving the difference, because maybe one of them is far away removed from the whole, and that one is driving the difference. Because the thing about ANOVA is that you need only one to drive the difference, and all of them will drive the difference. So how do you do it? That is where the post hoc test, after finding the significance, come into the picture. You can use some things called Tukey's HSD. Okay. You can use the Tukey's HSD to determine if the difference is being driven by a particular group. Sometimes you can use the Bonferroni test, okay, the Dance test, the Nemina test, the Neminis test. All of these tests can tell you. So each one will tell you. So the number, the tests are here. And after you've done the Kruskal-Wallis, you use the Dance test to test what is driving the difference. After you've done the Friedman test, you can use the Nemeni's test to test which is driving the difference. What is driving the difference? If you do the ANOVA, you can use that also, the Tukey's HSD, to test whether there's. I do this at the MPhil level, where I go into details. So, ladies and gentlemen, that is how you got to execute tests. So what I'm going to do is I'm going to let you be able to do some of these things in a huge data set I'll give you. Okay, this weekend, I'll give you that data set and I'll give it to you as an assignment for the group. Everybody will come in that group. It's a whole lot. Everything we've done, we'll address that. But in exams, I will generate some results and tell you to interpret, to formulate hypotheses, to explain, to use the results, to be able to come out with conclusive conclusions. Ladies and gentlemen, that brings us to the end of the entire caboodle. At this stage, if you have a question, feel free.